Hey guys, we're going to be going over 2018, the first free response question here. And each time I do it, I'm going to tell you what I think, and then I'm going to pull in the actual grading rubric off the website that I've given you a link to, which is what you guys should be doing to kind of train yourself on how to answer these questions. So this is a rotation question. Student experiment reveals that while the disc is spinning, friction between the axle and the disc exert a constant torque on the disc. That means it's going to be slowing down. And if it's a constant torque, this is how I'm thinking. The net torque on something equals I alpha. This is akin to Newton's second law. Sum of the forces equals ma, if you want to think in terms of linear motion. Where we don't like to have forces in rotation, we talk about torques. Masses become moments of inertia because where you place the mass matters. And linear acceleration becomes angular acceleration. Since that's a constant torque, you don't change the moment of inertia of the system without changing where the mass is. That means it's going to have a constant deceleration. All right, time t equals 0. It has an initial clockwise is positive, angular velocity of positive omega naught. So in the linear world, that would be like having a v naught. It later comes to rest. That means you have a v final equals to 0 in the linear world at time t1. Sketch a graph that will represent the angular velocity as a function of time. Okay, so we're starting out with an omega naught at time t equals 0, and we're coming to rest at time t equals 1. Since we said that it was a constant angular deceleration, that means you're going to have a constant, I'm trying to make a straight line, a constantly changing velocity all the way down to 0. Since the slope of that line is your acceleration, just like if this was a just regular velocity and regular acceleration graph, you would take the slope of that line to get to this line. You're taking the slope of that line to get to here. So, I don't know. Well, it's just negative. It's all right. It's not giving us numbers. So you have a flat line right here showing a constant whatever alpha. So I'm going right over here now to the guidelines, how to score it. This has no meaning to you. It's just showing you it's hitting all our state learning objectives. That's what LO is, I guess. We look like we did it right. Let's go over points. You get 1 point for a curve that has an angular velocity of plus omega naught at time t equals 0 and decreases to 0 at time t1. We did that. A straight line and a negative slope, we've got that. And it lets you go positive. It gives you 2 sets of answers here, just in case somebody used, like instead of clockwise as counterclockwise as positive, they use clockwise as positive. In case you make that mistake, they're not taking off for it. And for the acceleration time graph, you get 1 point for a negative line, and you get another point for a constant non-zero function. So you get to have to show that it's a constant angular acceleration, which is what we did. That's what the flat line shows. All right, second part. Magnitude exerts, I'll just read it. The magnitude of the frictional torque exerted on the disc is T naught. Derive an equation for the rotational inertia of the disc in terms given. All right, so I'm going to write what I wrote up top, that the net torque, which is T naught, equals I alpha. Solve that for I, you end up with I equals T naught over alpha. Perfectly accurate statement, not given in the allowable terms. These two I didn't hit. So how do I relate alpha to omega naught and t? Well, since like acceleration is your change in velocity over time, your alpha is going to be your change in omega over time. Since your final is 0, it's just omega naught over t. Plug this in here. You end up with I equals tau naught divided by omega naught, and then the t would come up top, times t. Nope, t1. I don't know if they take off of that or not. Did we hit all the points that you can get? Looks like there's two ways to solve this one. This is the way I did it. 1 point for using an equation for the rotational version of Newton's second law. That's what I started out with. Then you solve it. Oh, nope. Then you're going to see that you needed to solve for alpha in terms of omega and t. That's what we did. And the correct answer. Good. Got all 3 points. Totally different way to do it, using the fact that your angular momentum is going to change, and it's going to change with this formula. If this was linear momentum, it would be your change in momentum equals force times time. But in angular stuff, it's linear momentum. We don't like forces, we like torques. Time's the same everywhere. Okay. Another experiment. Disk again has an initial positive angular velocity, same as the first part of the question, omega naught at time t equals 0. So that puts us right here in the beginning. At half t1, the student starts dripping oil on the contact surface. So he's reducing the friction, reducing the torque. It's going to slow down slower. It's going to take longer to come to rest. Lost my spot. Actual to reduce the friction. As time passes, more and more oil reaches the contact surface, reducing friction even further. So it's continually changing the friction. So it's getting less and less friction over time. On the grid below, sketch a graph that could represent the disk's angular velocity as a function of time. All right, same as before. Which is the time it took, which is the time at which the disk came to rest in part A. So for the first part of this, nothing's changed. So I'm still drawing a straight line. Then, as time goes on, he just doesn't put one drop of oil on and changes the friction by a constant amount. He puts multiple drops of oil on. So it's getting, I'm curving this line because it's getting less and less and less friction, slowing down slower and slower and slower and slower, at a slower rate, I should say. Then on the other one, we got to do the acceleration. So the acceleration stays the same for the first part of the problem because it's identical. And then, since the slope of this line is changing, that means your angular acceleration is decreasing and decreasing and decreasing and decreasing. So these are all negative slopes, getting less and less and less negative, approaching 0. Getting less and less and less negative, approaching 0. I probably shouldn't have even hit 0, but I did. So let's see if I lost any points. For a curve with a clear change of slope or curvature at that point, which is what we did halfway through, and showing a decrease in speed thereafter. Okay, so I got a point for that. A curve that indicates slowing at a decreasing rate. Okay, at that between T1 over 2 and T1. I did that. I curved my line. So if you put a straight line here, just kind of bent, you know, showing that you understand that it's slowing down at a slower rate, you would have got 1 point, but not the second point. You got to show that it's curving. For a curve that does not reach 0, that's right, because if it's slowing down at a slower rate, it's not going to come to rest as quickly as it did before. Visually, it looks right. Let's see if I lost a point because I went to 0 there. Curve that is negative the entire time, it did that. For a curve that is a constant non-zero function. Okay, didn't lose a point because I had 0. Thought I was gonna. All right, last part, D. Oh, wait, I didn't go over the acceleration one. For a curve with decreasing magnitude between t over 2 and t, and I did a curve with decreasing magnitude. Because when you go from a negative number towards 0, you are decreasing. Remember, sign is just direction here. An acceleration that may reach 0. I got away with it. At or before time t1. So, got away with that. Last one. Students trying to mathematically model the magnitude of the torque exerted by the axle on the disc when the oil is present at time t is greater than t1 over 2. So that's in this section here. Student writes down the following 2 equations. Each one includes a positive constant C1 or C2 with appropriate units. So some constant. All right. Doesn't matter what it is. It's just C1 or C2. Which equation better mathematically models this experiment? Let's take a look at one. All right. Torque well, this would say, this would be adding a number to your torque. This would be saying like this constant times some positive number is going to give you increasing torque. That's not happening. Over time, as time goes by, yeah, this should be in the denominator, because as time goes by, the torque is decreasing. So we got to go to equation 2, because it shows, I'm not going to write it out, that as time passes, the torque decreases.